Hello, everyone. Today we are going to have Kristiansen Lara. He's from uh, a postdoc, right? Sorry,
Yes,
Kristiansen,
a
I didn't
postdoc.
ask. A postdoc, yes. A student from the Centro de Estudios Científicos de Valdivia. He's going to speak about the formation of AdS3 boundary conditions within the integral system scheme. So, Kristiansen, go ahead.
Thank you very much. Well, first of all, I would like to say thanks to the organizers who kindly gave me a spot on their seminar schedule. Thank you very much. Well, as the title says, this talk, its title is Deformations of AdS3 Boundary Conditions within the Integrable System Scheme. My name is Kristiansen Lara, and this work was done in collaboration with my former PhD advisor, Miguel Pino, and my friend and colleague, Francisco Reyes, who's now finishing his PhD with Miguel. So if I will have to summarize my talk in some brief and simple lines, is that here we are going to address a novel duality between, on one side, general relativity in 2 plus 1 dimensions with negative cosmological constant, namely AdS3 GR, with, on the other hand, integrable hierarchies, concretely what is known as the dim hierarchy, and how we are going to connect, how we are going to link these two different worlds. It is going to be addressed with the imposition of suitable boundary conditions for the gravitational field within the Chern-Simons formulation of AdS3 GR. In this regard, let me start by speaking about some perspectives and paradigms. Well, we know that the unification of space and time as a single entity is one of the hallmarks of the 20th century physics, which lead to general relativity. And general relativity is a very beautiful theory. It is very consistent from the theoretical and experimental point of view. So this paradigm for the 20th century evolved into the 21st century to what is known as the holographic principle, which was conceived originally by Thott, Thorne, and Susskind in the 90s. And it states the following, that the dynamical content of a d-dimensional gravitational theory is encoded on its d-1 surface volume. And although this was developed for GR, it was soon generalized for gauge theories. And in this regard, its first concrete realization was done in a string theory context, known as the AdS-CFT conjecture, proposed by Maldacena in 1998. Although this is a very successful example, I would like to emphasize the work of J.D. Brown and Brown-Henneaux, which almost 10 years before that this successful example was realized, they proposed that with the imposition of suitable boundary conditions for GR on AdS3, the theory exhibits asymptotically two independent copies of the two-dimensional Virasoro algebra with the Brown-Henneaux central charge. Here, L is the AdS3 radius, and G is the three-dimensional Newton constant. So the lesson is that this lower dimensional result emphasizes the role of the asymptotic behavior of fields in order to elucidate holographic properties of gauge theories without relying on string theory. So, following the lead of Brown and Henneaux, we aim to explore novel asymptotic behavior in AdS3 GR to establish new holographic correspondences. But before that, we are going to review some aspects of AdS3 GR. And it is the fact that AdS3 GR is inherently a holographic theory. And let me argument this point. First, AdS3 GR, and to be honest, 2 plus 1 general relativity in general, is a trivial theory from the bulk perspective, namely that the Riemann tensor may be fixed in terms of the Ricci tensor. So every solution of Einstein equations will locally coincide with the value of the cosmological constant. Therefore, there will be not bulk propagating degrees of freedom, such as gravitational waves. So this seems a disappointing fact from this theory. Nevertheless, the theory admits a black hole solution known as the BDZ black hole, which corresponds to an improper identification of AdS3. And also, it is important, as I was saying at the beginning, to emphasize the role of boundary conditions. Boundary conditions are important. Why? Because they allow us to define asymptotic symmetries. And asymptotic symmetries correspond to the set of gauge transformations that preserve the form of boundary conditions. And moreover, in the work of Cousin, Henneaux, and Mandril, the authors, with the imposition of the Brown-Henneaux boundary conditions, unveiled that the theory, although it is topological from the bulk point of view, it exhibits asymptotically boundary degrees of freedom, propagating degrees of freedom at the boundary. And in this regard, there has been some applications of this fruitful toy model, which one of these is the soft hair proposal from the MS translation symmetry of Hawking, Perry, and Strominger, also the celestial holography program. And important for this talk is the duality between integrable systems and general relativity. It is important to mention that the first example that revealed this duality was given in the article of 2016 of Perez, Tempo, and Troncoso, and therefore this duality was explored in different contexts, for example, on higher spin gravity, recently to a broader family of boundary conditions known as the AKNS system, and more recently in its two-dimensional downlift. This is an article like 2 weeks ago, perhaps. So it is something that people has been exploring. So now let me do a crash course on integrable system in order to prepare ourselves to understand the topic that I aim to address. So many differential equations that appear in nature, many of them are nonlinear. So with nonlinearity, the superposition principle does not hold here, and the mathematical procedures are more harder or even impossible to perform. However, many of these nonlinear system of PDEs, of partial differential equations, are integrable. And what is the definition of integrability? I am going to address here in this point. So, but for concreteness, we are going to study a toy model, a very known example, a toy model known as the Korteweg-de Vries equation. It is given by the following equation that you can see here, where L is the dynamical function that depends on t and phi. L dot is the derivative with respect to the time, and primes are the derivatives with respect to phi. I forgot to say that, please, if you have some questions, do not hesitate to ask me. And here, L is a constant with dimensional length, which from the GR point of view will correspond to the AdS3 radius, and L will correspond to the boundary propagating gravitational degrees of freedom. But for the moment, let us focus here. So we have two ingredients in this equation. The first is that we have a nonlinear term, and secondly, we have a dissipation term. So nonlinear and dissipation are fighting to each other in this equation. So the KDV equation, and concretely integrable systems in general, it's a very miracles can happen in this topic. Let me show you why. The KDV equation admits a big Hamiltonian formulation. So first of all, notice that the KDV equation can be rewritten as a conservation equation. So we have this equation that you can see here. Nonetheless, observe that this quantity here may be recognized as the functional derivative of some quantity H2 with respect to L, and we arrive to this quantity here. So on the other hand, we can rewrite the KDV equation in this form. we can read this guy as the functional derivative of h1 with respect to L, and we arrive to some h1. So in sum, we were able to rewrite the KdV equation in two different forms, concretely like this. So we have some differential operator d1 acting here and d2 acting here. This is what is known as the B-Hamiltonian formulation of some nonlinear PDE, and here h1 and h2, and there will be many others. I'm going to explain it in a little bit. They are known as Hamiltonians of the theory. Okay, so we have this form to rewrite the KdV equation. So now with operators d1 and d2, we define the following Poisson brackets, or more, in a more succinct way, it is possible to define a symplectic structure. So it is important to show that the Poisson brackets are well defined, namely that they are Poisson brackets. So if they are Poisson brackets, they have to fulfill three properties, right? The first is that they are antisymmetric. Secondly, the Leibniz rule, and finally, they fulfill the Jacobi identity. If these three properties are hold, we have a well-defined Poisson bracket. Also, it is important to show that the Poisson brackets are compatible, namely that the linear combination of these two Poisson brackets yields a third Poisson bracket that is also well defined. So
Kristiansen.
now, sorry, please.
Yeah, sorry. Does this mean that the phase space is like a product, like a geometry product between two phase spaces or something like that?
No. It's no. Let me finish the point, because
Okay.
Perhaps it will be more clear if I reveal what is the definition of integrability.
Okay.
Because I can give you, if you want, in terms of the Arnold-Liouville theory, but please a little bit.
Yeah.
So a system. Sorry.
I have a confusion because you have two Hamiltonian, right? So if I
Yes.
think that one of them is just a Hamiltonian, the other is some conserved charge, can I think in that way, or just
I haven't shown that they are conserved. Okay, I spoiled you with the definition of Hamiltonian, but I never told you that they were conserved at the moment.
So you just use like the okay, they are just Hamiltonians. Okay.
But I'm going to show it, but wait a little bit. Just be patient a little bit. So a system will be Hamiltonian if and only if we can find the two compatible, well-defined Poisson brackets, and that's the definition. So in a more non-rigorous definition is that you are able to find these guys. This relation between D1, D2, H2, and H1. That's it. Okay, it has some subtleties, of course, we can discuss it if you want, but that's the rough definition. Okay, I am going to give a second example anyway.
Yeah, maybe my confusion is if I have two Hamiltonian, maybe I would say maybe there are two times, and that is kind of way.
No, because you can define time evolution with the two symplectic structures, so there's nothing wrong. Everything's okay. You can define time evolution with H1. It's okay. Under the first Poisson bracket 1, and then you can define time evolution with the second Poisson bracket. That and to be honest, that's the definition of this. Because in terms of the Poisson bracket, this guy, D1 variation of H2 with respect to L is the Poisson bracket between L and H2. And this guy is the same.
So should I think that I have two times, or just there is just one?
No, you don't have two times. No. You have two different symplectic structures when time evolution are produced in the same footing from these two symplectic structures. That's it.
Okay.
But I am going to show you. But I am going to show you the definition of integrability, and it seems that maybe that will solve your question and also from Matthias.
Okay.
Sorry, I have another question. One of these Hamiltonians
Yes,
can be thought as the deformation of the Lagrange or something like that.
Sorry, I can't hear you well.
Okay, sorry. What I'm asking is if one of defined could be thought as the general transformation of the Lagrangian, or that it doesn't match with anything like that?
Yeah, that's a very interesting question. It happens that for integrable systems, there are no local Lagrangians. So it is a problem. However, Pérez Tempo and Troncoso, they found a way to obtain some Lagrangian for integrable systems, but it has some subtleties like zero modes and that kind of things. But it is well known from the literature that Lagrangians for integrable systems, they are not local. You have to plug some Heaviside step function inside.
Okay. Thank you very much.
No, thanks to you. So, okay, we rewritten the equation, the KdV equation in this fashion, where H1 and H2 are given by this expression and D1 and D2 like this. And observe that it is possible to show by induction that this B Hamiltonian relation can be extended to include some general Hamiltonians n+1 and n. So this corresponded to a differential equation, and this differential equation can be solved, and it is possible to show that it is possible to find that H0 is given by this expression, H1, H2, H3, there are infinite of them. Okay, so with them, I am going to prove the integrability of the system in the Liouville sense. Okay, there are many definitions for integrability. I am going to give you the definition of Liouville. So here it comes. For example, think about in the Kepler problem. In the Kepler problem, you have to solve the integral of motion. In order to do that, you have to recognize the energy and angular momenta of conserved charges, and then you are able to solve the integral. Here is like the same story, but here you are dealing with a field theory. So instead of having two conserved quantities, you will have infinite of them in order to solve the integral of motion. So I think that solves perhaps Robinson's question. So now regarding Matthias' question, Matthias was asking me if we have two phase spaces, but now I show you infinite Hamiltonian. So perhaps one can say that, okay, there are infinite phase spaces. No, the answer is that, but I have to introduce some symplectic geometry, is that from the symplectic geometry point of view, if you compute the Lie derivative of the symplectic structure, you will show that it will be zero. So in other words, it will be a symplectomorphism, namely a canonical transformation. So in other words, the successive Hamiltonians implies the existence of many canonical transformations that allows you to solve the system. So you have the system in a very difficult form, and then after successive canonical transformations, you are able to solve it in Darboux coordinates, as it is known. And that theorem is known as the Arnold-Liouville theorem, to be more concretely. I don't know if that solved your question, Matthias.
Yes, excellent. Thank you.
Yeah, solved my question as well. Yeah, because it's basically instead of thinking that it's just canonical transformation, you have infinite of them that will generate that time to.
Yes, but exactly, there are successive canonical transformations. That's it.
Yeah.
So now I am going to show the integrability of the system. Well, the integrability of the system, it is given by the following expression. Integrability means that we are able to solve the integral of motion. So if we are able to solve the integral of motion, then it means that the system is integrable in the sense that we can solve the integral of motion. So the time derivative of Hn is given by the Poisson bracket 1 and 2 of Hn and Hm. However, for simplicity, I am going to work along with only the first Poisson bracket because the proof is analog for the second one. In this regard, the definition of the first Poisson bracket is given by this expression that you can see here. Nonetheless, observe that we have this recursion relation. And within this recursion relation, if we apply D1 on Hm, we will obtain D2 of Hm minus 1. Do you agree with me? So if we have this expression here, notice that this guy is by definition the second Poisson structure. But because the Poisson brackets are well defined, it is antisymmetric. And due to antisymmetry, by definition, we arrive to the second Poisson bracket. And again, we apply the recursion relation. So D2 acting on Hn, we will obtain D1 acting on n plus 1. So we are going to jump to the first Poisson structure. We obtain this, and this is equal to this guy. And this guy by antisymmetry is this guy. I don't know if I was too fast, but I hope it is clear. So we arrive to this guy here. So now we can apply the same procedure m minus n times, and we will obtain this Poisson structure. And this Poisson structure, remember, it is equal to this guy, right? So I think, as for me, it is clear now that is 0. Therefore, for the second Poisson structure, the proof is the same, is in the same spirit. So we arrive to the definition of integrability is that we have infinite conserved quantities, and these infinite conserved quantities are in involution. Namely, the conserved quantities Poisson commute under the first and second Poisson structure. And that's the definition of integrability in the Liouville sense. So, as I was saying, we have infinite conserved charges, and they all Poisson commute with each other under the first and second Poisson structures, namely they are in involution. Well, we had, as I was showing, we had an infinite amount of conserved quantities, so we can rewrite the complete KdV hierarchy in this form, because we have the Hamiltonian recursive relation between one and each other, and therefore it is possible to write the complete KdV hierarchy. Notice that for n equals to 0, it is trivial. For n equals to 1, it's important this example, since n equals to 1, it is known as the chiral boson equation, which correspond to Einstein equations within the Chern-Simons formulation of gravity for the Brown-Henneaux boundary conditions. Secondly, we obtain the KdV equation, and for n equals to 3, we arrive to this horrible expression. And for n equals 17, the equation is horrible. But the miracle happened is that we possess a very huge underlying structure that allows to study the system consistently. Well, but this is not the only features. The second one is that it is possible to construct analytic solutions by hand, only with paper sheet and pen. And one of them are solitons. And it is important, this point is that solitons emerge as a fine-tuning between the nonlinear term of the KdV equation and also with the dissipation one. If you crash these two phenomena, you will emerge with a soliton. That's the definition of the soliton. So one could ask, okay, so the superposition principle holds here, and the answer is yes, the superposition principle holds, but it's nonlinear version. And you can see it here by the KdV to soliton. Observe that we have the soliton coming and crashes with the other soliton and emerges from the collision on change. And that's the definition of a soliton indeed. The definition of a soliton is that it is a solitary wave that can interact with another soliton and emerge from the collision on change up to a phase shift. And you can see the example here. So as I was saying, miracles happen. So there is another miracle in this topic, and it's the zero curvature formulation. And this is the connection with Einstein equations and SL2R. So consider the two-form curvature, this guy that you can see here. So if for the KdV example, if I specify the following gauge fields AT and A phi in the following form, where L is the function that depends on T and phi, and L1, L-1, and L0 are the generators of the SL2R Lie algebra, it is possible to find that the zero curvature equation yields the KdV equation. And this is the principle that we are going to extrapolate to introduce different integrable systems. So this is the zero curvature. And the zero curvature in the Chern-Simons formulation is the Einstein equations. So this is the reason why we have integrable systems general relativity. This will be the linking point where we are going to connect these two different worlds. In the Chern-Simons formulation, the gauge fields AT and I phi, they will correspond to boundary conditions for the gravitational field. So this and the discussion. So for more concreteness, we are going to give another example, which is the Dim equation. So the Dim equation is this nonlinear PDE, is horrible, as you can see here. It has some square roots. Nonetheless, it is possible to rewrite the Dim equation in the following form. So it is magical, in my opinion. So we have this guy, and this guy can be rewritten in a big Hamiltonian form. So we have this operator acting on the variation of H0 minus H1, and this operator epsilon on the variation of H minus 1, H0, where D is given by this guy, epsilon by this guy, and H minus 1 is given by this non-local quantity, but non-local quantities in the integrable systems literature is very common, to be honest. It's a very common thing that happens. And H0, H1, and with this, it is possible to show that we have a big Hamiltonian system, and the operators satisfy the recurrence relation, just like the KdV equation, but the difference lies in the form of the operators D and epsilon and the form of the Hamiltonians, but it's the same spirit. And with them under Poisson brackets, we define the first Poisson bracket D and the second Poisson bracket epsilon. It is possible to show, just like as the previous example, that the time derivative of H, or I would like to say it in this form, that the conserved charges Poisson commute with each other, namely they are in involution, unveiling the integrability of the system. So Dim equation is what we are going to work along with this talk. So finally, a simple solution to the Dim equation, which correspond to a black hole solution that we are going to construct. It corresponds, for example, a simple solution is L equals to constant. So if L is equal to a constant, the time derivative vanishes, and this guy at the right-hand side vanishes too. So we're done with this. Nonetheless, observe that there can be more complicated solutions, and there is a complete industry that works on it, and it is a topic on its own. It's very profound and it's very difficult, and there are methods that generalize the nonlinear superposition principle. So if you want, we can discuss it. So therefore, we are in position to define the general objective of this talk, which is to unveil the equivalence between Dim's hierarchy and the asymptotic dynamics of AdS3 General Relativity. And particularly, we are going to impose boundary conditions to the gravitational field, all in the Chern-Simons formalism. We are going to show that these boundary conditions are suitable, and we are going to recover a black hole from the boundary dynamics and study its thermodynamics. I would like to emphasize that in this talk, I am going to use Hamiltonian methods. So this is the table of contents. I don't know if there are some questions relating to the first part of this talk with the introduction.
Yeah, all of this story of integrability is something just classical of quantum? Okay, it can be.
This is classical integrability. Yeah, because if you want to reach quantum integrability, you have to fulfill the Yang-Baxter equation.
In normal AdS CFT, we think that the ball is dual to a quantum theory. So in this context, how should I understand this like duality between?
No, because within this, it is possible to obtain a boundary. It is possible to obtain a boundary theory, a theory on the reduced phase space that captures the boundary degrees of freedom of the integrable system. This has been done in the articles of Perez, Tempo, and Troncoso, and then you can quantize the theory. Canonical quantization because it will be a gauge theory, a gauge scalar theory. You will have some constraints, or you will have some zero mode. So it is possible to quantize the theory. However, we are dealing right now with non-linear equations, so the quantizations is not trivial. However, I would like to emphasize that for the KDB example, it exists its quantum version.
Okay.
So to answer concretely your question, yes, this is going to be a semi-classical discussion, not quantum. But if you want to estirar el chicle, I don't know how to say in Spanish, you will have you must consider the boundary theory, and with the boundary theory you study the Poisson structure, the Hamiltonian structure, and then you can quantize it. It is possible, it has been done. So, okay, GR on AdS3 and the Dean's hierarchy with the Hamiltonian perspective. And so, as shown by Achúcarro, Townsend, and Witten, in the vacuum and with negative cosmological constant, AdS3 GR can be written as the difference of two Chern-Simons action. Here, K is the level of the theory, L is the AdS3 radius, J the three-dimensional Newton constant. The manifold is foliated in polar coordinates, and the gauge fields A are spanned in two independent copies of the Lie algebra, G plus minus, where G plus minus are correspond to the SL2R Lie algebra. So the equations of motion are given by the zero curvature equation. This is the linking point with integrable systems. However, before addressing this, let me study some aspects of the Hamiltonian formalism. So consider the 2+1 splitting, as you can see here. So in components, and if you perform the Dirac-Bergman analysis of constrained analysis of Hamiltonian system, it is possible to obtain the Hamiltonian action of the Chern-Simons action given by this expression here. Notice that we have this constraint of the theory Fij. Fij is a constraint of the theory that vanishes when we impose the equation of motion, and He is a Lagrange multiplier. Regarding this term, the boundary term B, well, if we want a well-defined variational principle, we must supplement the action with a surface integral, whose variation is given by this expression that you can see here. Therefore, remember that AT is a Lagrange multiplier. We must specify suitable asymptotic behavior of AT and A phi in order to integrate the boundary term. But as I was saying, AT is a Lagrange multiplier, so it's not constrained by the equations of motion. So you have to be, in principle, it seems very naive to introduce anything that you want on AT. Nonetheless, the criteria to introduce the asymptotic behavior of AT and A phi is very subtle. One of them is that you have to integrate the boundary term such that you are able to, you're rendering differentiable Hamiltonian action principle. This is, by the way, the same problem when one wants to compute the Gibbons-Hawking-York term. It is the same. For the Gibbons-Hawking-York term, you only impose Dirichlet boundary conditions. But it's the same spirit. In fact, the Gibbons-Hawking-York, yes. So it's the same story. So before proceeding, we can vanish the radial dependence through a gauge transformation. In 2+1 general relativity, the radial dependence is pure gauge, so it is possible to gauge away it. And if we perform the following global gauge transformation for the gauge field A, here I will refer lowercase a, I will refer it as the auxiliary field, auxiliary Chern-Simons field. If we perform the following gauge transformation, where B captures completely the radial dependence of the theory, the variation of the boundary term transforms under gauge transformation in the following form. However, observe that due to the cyclic property of the trace, the red terms cancel and the middle terms also too. Therefore, we arrive to this expression here. So the radial component is not necessary. Where here A, AT dt plus A phi d phi only depends on T and phi. The radial dependence gauge away. So now we have the motivation to impose boundary conditions. And these are given by Bunster-Henneaux, Perez, Tempo, and Troncoso, given by this expression here. However, these are not the complete set of boundary conditions. The complete asymptotic behavior will be completely specified in the choice of these Lagrange multiplier functions mu. Remember that HE was a Lagrange multiplier, so these functions are, I'm going to refer to them as Lagrange multiplier functions. So before inserting the boundary conditions in the boundary term and see if the Hamiltonian action integrates and it is well defined, we have to delve first into the construction of the gravitational asymptotic dynamics. So we have to perform some intermission before plugging the boundary conditions on the boundary term in order to explore the asymptotic behavior. So remember that after a gauge transformation, the gauge field transform in the following form. So the zero curvature equation will transform in the following form. As you can see here, B1 and B vanishes, so we arrive to Einstein equations rewritten in this form. Thus, so with the boundary conditions with HE and A5, the zero curvature reads in the following form. I would like to emphasize that this will yield the dim hierarchy, but the difference is that we have this plus minus here, plus minus. It is the only difference. So we will have two copies of Dim's hierarchy. That's it. It's the same story as before. So this equation of motion, we are going to rewrite it in the following form, where D and epsilon are given by these operators here. And C was a redefinition of the Brown-Henneaux central charge that you can see here. So now we have to choose the form of the function mu. Remember that mu was belonging to AT and AT was a Lagrange multiplier. So we have to impose the form of mu, and inspired in the work of Ablovitz, Kaup, Nibel, and Seeger to solve nonlinear PDEs, we are going to consider the following polynomial ansatz in this reduced central charge like this. So we are going to consider mu as mu0 plus a summation on this central charge given by this expression. So we're going to consider some deformations of the Brown-Henneaux boundary conditions. Why Brown-Henneaux? Brown-Henneaux boundary conditions are obtained if we choose mu equals to 1 here. If we choose mu equals to 1, we have A5, this guy vanishes, so we will have A5, and AT will be proportional to A5. So with the boundary conditions that we are going to choose with the election of mu, like this, we're going to deform the Brown-Henneaux boundary conditions. And that's the spirit of this talk. Robinson, please.
Yeah, I have a question. It's just to understand this because I'm familiar with the metric formulation. This Lagrange multiplier of the Scherr-Simon would be kind of like the sheaf and the lapse in the metric formulation, right?
Yes, exactly.
So basically, we are saying that those two Lagrange multipliers must have certain boundary condition in infinity to do whatever you want.
Exactly. To be more concrete, we are deforming the lapse function, and that's it.
Okay, got it.
But we are going to work with the metric formulation too.
Okay, got it.
Okay, so if we specify the following Lagrange multiplier function mu in the following form, we will obtain, if we replace this guy here in the above, here in this equation, we are going to obtain a lot of equations. However, notice that these two terms, they depend on, they are the coefficient of c power 0. While this guy here is the coefficient of c minus 1, and this guy also depends on c, and this guy too. So we can equate order by order in c. And this is what we are going to do. So we obtain this equation that you can see here, this condition here, which resembles the B Hamiltonian recursive relation, and we obtain this. I would like to emphasize that to obtain the operators that yield a well-defined B Hamiltonian structure, is not easy. It's not an easy task. I showed you for the KdV equation, but it is a lifetime problem. It is a lifetime problem. If you have some nonlinear PDEs and you want to rewrite it in a B-Hamiltonian fashion, it is a very hard problem. So the power of this method is that with this method, we automatically obtain the B-Hamiltonian relation for the hierarchy. So we obtain this equation that I was saying, and notice that, of course, we can rewrite n and n plus n minus 1 in order to not begin this recursive relation for n greater or equal than 2 to start from n greater or equal than 1. It's just a redefinition. So now this corresponds, as I was saying, to the equation of motion, and this guy here and this guy here, they correspond to some initial conditions for the functions mu0, mu1. And this guy, as I was saying, corresponds to the B-Hamiltonian recursive relation. But as I am trying to emphasize, this was obtained automatically just by this ansatz. It solves the integrable problem immediately. It's like God gifted to obtain this structure. So we start to solve the initial condition, and remember that epsilon was a third derivative operator, and we obtain the solution. However, we are working in polar coordinates, so everything that we have here has to be periodic. So all of these functions has to vanish. So I am going to conveniently fix mu0 equals to some, it can be fixed to alpha 0, for example. So alpha 0, I am going to fix it to 1 in order to make touch with the Brown-Henneaux boundary condition. Remember that Brown-Henneaux boundary conditions were given for mu equals to 1. So now we have the mu1 equals to 0. Again, this is a PDE for mu1, and the solution is given by this guy. This is mu1, and that's it. So we have mu0, mu1, and now we have to understand what does it mean, this relation. Well, this relation, to be more concrete, I am going to fix n equals to 1. If we fix n equals to 1, we have this PDE for mu2. So we know mu1, yes. So if I know mu1, I can know mu2. So the solution of this is given by this guy. And that's it. And also one can perform the procedure for n equals to 2, and you obtain this guy. A horrible expression, but analytically. Notice the following, that mu1, forget about alpha 1. You have mu1 is 1 over 2 square root of L. So for mu2, you have like mu1 here, because you have 1 over 2 square root of L, plus a new term. So it's like that the guys, they are coupling with each other, with the next one. So for example, let us emphasize on mu3. On mu3, you have mu1 here, as you can see here, but also you will have mu2. You can compare with the guy above, and they are the same. But now you obtain a new term. So in principle, it's like mu n, it will be given by mu n minus something, and then you're going to add it to obtain the one that is desirable. I'm going to write it. So, for example, for these two examples, notice that this quantity, 1 over 2 square root of L, can be rewritten as the variation of H1 with respect to L. Why? Because H1 is given by this guy. So if you perform the functional derivative of the square root of L, you will obtain precisely 1 over 2 square root of L. And the same story goes for mu2, mu3, and so on. So in general, it is possible to write mu n as the following summation. So that's the lesson. But in principle, it is proportional to some functional derivative of h with respect to L. So now, because mu is equal to mu0 plus this guy here, and mu0, remember that was chosen such that mu0 was 1, the function mu in total read as this double summation. But for simplicity and pedagogical purposes, we are going to choose alpha n minus I plus 1, like a delta, like a Kronecker delta, and we are going to obtain this expression. So the take-home lesson is that mu is proportional to the variation of h with respect to L, and that's it. And that hypothesis will render the boundary term integrable, and therefore the Hamiltonian action will be well defined, and also will induce charges and mass and angular momenta, which I am going to talk right now. So this will be the form of mu that we are going to work with. I don't know if there are some questions at this point. Okay. So replacing the values of mu in the equation of motion like this, we will obtain the hierarchy, the Dim's hierarchy. These equations we are going to write. So it is direct. If you replace the form of mu, mu1, mu2, mu3, and so on, you will obtain this equation, the chiral boson equation, the chiral boson with a deformation known as the Harry-Dim hierarchy, the chiral boson minus another deformation, and so on. This is the reason why this work titles is Deformations of AdS3 Boundary Conditions. We are deforming the Brown-Henneaux dynamical asymptotic dynamics. We obtain the Dim's hierarchy, as I was saying. So regarding the Hamiltonian recursive relation, it can be rewritten in the following form. And therefore, if we define the Poisson bracket D and the Poisson bracket epsilon, it is possible to show that the charges Poisson commute with each other, therefore arriving to the definition of integrability in the Liouville sense. I hope that it was clear with respect to the introduction, the crash course on integrable systems. So now we return to the boundary term. We were aiming to impose boundary conditions and to integrate the boundary term. This was the boundary term. And with the asymptotic behavior mu given by this expression, so the boundary term that renders the action differentiable was given by this expression. So if we introduce AT, A phi, and mu, we have this guy. But notice the following: mu is proportional to a functional derivative of h with respect to L, right? So this, we will have variation of h with respect to L, variation of L. By the chain rule, it is nothing that the variation of h. Therefore, the boundary term will be proportional to h, like this. Therefore, the take-home lesson, the take-home message is that the conserved quantities of the integrable systems maps to the gravitational charges, for example, because one associates the boundary term to the energy, the mass, they map to gravitational quantities. The boundary conditions therefore yields a well-defined action function. So regarding the asymptotic charges, I am going to skip the details regarding this, but the boundary conditions produce the following charges. Q0 is equal to the zero charge of the dim hierarchy, Qm to the m charge of the dim hierarchy. And here m can take any positive integer value, not necessarily equal to n. I would like to emphasize something here, is that when we consider the boundary conditions, when mu expanded in terms of from n equals to 1 to capital N, we are considered a huge infinite family of boundary conditions labeled by this number n. So in principle, we are dealing with an infinite family of boundary conditions parameterized by this number n. So the asymptotic algebra is given by this formula here, and concretely, as expected, the involutive nature of the dim conserved quantities maps to the algebra of gravitational charges such that it is infinite dimensional and it is abelian. And the same story goes for Q0 and Qm. The Poisson bracket between these two guys will also be zero. So as I was saying, to summarize this point is that the involutive nature of the conserved quantities maps to the gravitational algebra, to the asymptotic symmetry algebra of gravitational charges. As I was saying here. So now we go to the construction of the metric. So from the Chern-Simons point of view, if you have the gauge fields A mu plus and A mu minus, it is possible to construct the metric according to the following relation with the following gauge parameter B. If we specify the following gauge parameter, we write the following metric, which is a horrible expression, but it will be reduced, it will be simplified a lot in the following. We obtain the following metric. However, to encompass black hole configurations, we are going to consider a solution of Dim's hierarchy, which was, as I was saying before, L equals to a constant. So with L equals constant, which implies that mu, remember that mu was a summation of the functional derivatives of H, but H depends on L and its derivatives. So also mu will be a constant. So in this regard, the metric reduces to this expression. So this is the metric that we are going to work with. So notice that this metric is in very bad coordinates. So we are going to redefine this part of the metric like this as a big R squared in order to rewrite it in Schwarzschild-like coordinates. So in Schwarzschild-like coordinates and in ADM coordinates, because I'm going to write in Hamiltonian formalism, we obtain the following line element. So observe that n is given by, the Laplace function is given by this guy, f, the function that it is in the spatial part, along with the temporal one, is given by this guy, and also the shift by this expression that you can see here. We can reduce to the Brown-Henneaux case, which in this case yielded the Bañados metric, and the Bañados metric is recovered when mu is equals to 1. If mu is equals to 1, this term, this deformation term disappears, and we obtain, and this term also converts to 1. So the Laplace here transforms to f, and you will obtain the Laplace here and here. So as Robinson was asking, this is a deformation of the Laplace function. And also it has a deformation on the shape, yes. So we emphasize the fact that L is a solution of the stationary dim hierarchy. So the dim hierarchy, the first two guys of the hierarchy were given by this guy. So we have derivatives on the left and right hand side. So L equals constant is always a solution. So now we are going to study some gravitational aspects from the metric and the Hamiltonian, always from the Hamiltonian perspective. And we finish this talk. I don't know if there are some questions.
Yeah, I have a question about because you write on that almost like BTC black hole. But
yes.
Normally, I think that the BTC black hole just has one mass and one angular momentum, but now you have so many shards that I kind of get confused.
No, I am going to define the mass and angular momenta, and in that point is going to be clear. Yeah, because I have everything is in terms of these modes, L plus and L minus, and you don't know what thing is. And we know that because we are working on AdS3 GR, this is diffeomorphically equivalent to the BDZ black hole, but good luck to finding the the coordinate transformation. That's not a trivial problem. So okay, from the metric point of view, recall that in ADM coordinates the metric was given by this expression with the Laplace and shift functions defined here, and the horizon radius is defined like this. So one can ask for extremality, which is given by the condition when this term vanishes. And this term vanishes, for example, when L plus is equal to 0 or L minus is equal to 0. However, notice that the dim equation, and to be more precise, the complete dim hierarchy always has some square root in the denominator. So if you want to reach extremality, this equation, if L is equal to 0, it is not a solution of Dim equation because you will have a division by 0. So therefore, extremal black holes will not be included in this space. One can see it immediately. So regarding the mass and angular momenta, one can use its favorite method to compute the mass and angular momenta. One can use, for example, the covariant phase space approach. We use the Hamiltonian approach in the Chern-Simons formulation of gravity, and we obtain this following mass and this following angular momentum. So observe that, for example, for the Valdivia metric, one can invert the relation between L and M. So here it is not trivial to do this. So the black hole solution spectra is divided in the following. So this is the phase space of the black hole that we have. Notice that we have some dashed lines. And these dashed lines represent the extremal configuration that we will never be able to reach. Why? They were not permissible since the solution L equals to 0 is not allowed in the DIMS hierarchy. So inside here in the area, we will be able to have black holes. So regarding the definition of Hawking's temperature and the velocity of the horizon, it can be given, for example, by an Euclidean analysis. One can obtain the Hawking's temperature by the surface gravity if you want. But by the Euclidean analysis, you perform the weak rotation, and the absence of conical singularities implies that the Hawking's temperature is given by the following expression that you can see here. And notice, please, that we recover the standard result for the Brown-Henneaux boundary conditions or the Valdivia metric. When mu is equals to 1, we recover the same result. And for the velocity of the horizon, we obtain this guy. And observe that for mu equals to 1, this term converting in 0 vanishes. So regarding the thermodynamic analysis of this black hole, the variation of the boundary term in the Hamiltonian formulation, ADM formulation, for AdS3 General Relativity, the boundary term, I would like to emphasize that this is the same as the Gibbons-Hawking. It's analog to the Gibbons-Hawking, not the same. We obtain this expression here, where P is the canonical momenta, Nj is the lapse, is the shift function, and this guy is the shift function. Sorry, this is the shift and this is the lapse. And here the lines correspond to spatial covariant derivatives and gamma ij to the spatial metric. So in this regard, if we replace the thing that we have to plug, we obtain this expression here, which correspond to beta times the free energy of the theory. This imaginary complex number allows us to interpret this result in the saddle point of approximation as the logarithm of the partition function, and then you are able to compute, then you are able to perform some statistical mechanics on this. Here, the entropy from the canonical point of view, we use the Hamiltonian approach to this. So the entropy will be given by this expression here. So as you can see here, this corresponds to the Bekenstein-Hawking area law as expected, because we're working with general relativity. This black hole is diffeomorphic to the beta set black hole. I thought that the zero modes, the mathcal L, are not invertible in terms of M. So nevertheless, the black hole behaves well, although we don't have an extremal one. So in summary, we have shown the construction of dim boundary conditions for AdS3GR and established a well-defined nature in the sense that they allow for a well-defined variational action principle. They render finite and non-vanishing charges. The asymptotic symmetry algebra is infinite dimensional and abelian. And also it encompasses some interesting solutions such as black hole configurations, but not its extremal version. Finally, I would like to emphasize that the Bekenstein-Hawking area law holds. And future prospects, well, one can notice that the DIMS hierarchy possess anisotropic scaling. And anisotropic scaling is part of a more broader story known as Lifshitz holography, since for anisotropic scaling, one can compute an anisotropic generalization of the Carnot formula, which is compatible with the anisotropic scaling. So one may obtain a generalization of the Carnot formula. It is possible. We are working on it. And it is desirable to obtain a non-trivial solution to, for example, the equation. Remember that mu0 was equals to 1. One can perfectly define mu0 equals to 0. And with mu0 equals to 0, we obtain this equation here, which is also referred as Dim's equation. There are two versions of Dim's equation. One can perhaps solve this equation and obtain a soliton and study the geometrization of the soliton, in the sense that if we have this metric, if we have this, for example, no, but this metric was given for constant L for the zero modes. So if we have this horrible metric, one can replace the value of L and mu as solitons. For example, one can simplify the metric in order to lack of angular momentum. Angular momentum will vanish if L plus is equal to L minus. But if you replace L by a soliton, then you will be able to construct some metric, non-trivial metric with a geometrization of a soliton. But this is a future prospect. Finally, it is desirable to obtain a Hamiltonian reduction, as Robinson was suggesting, to obtain the boundary description of the theory, to make concrete the holographic part of the theory. So this was done in the article of Perez, Tempo, and Troncoso, but not with the Dim's boundary condition, of course. It was given for the KDV boundary conditions. So it will be desirable to obtain a field theory of boundary degrees of freedom and to compute, for example, the entropy from an asymptotic growth of states and a Strominger of the article of 1999 and analyze semi-classical properties. The quantum ones, I don't know, because I will be honest, I don't know how to quantize the KDV equation, but as far as I know it is possible. There is an article of Frenkel, I remember, maybe I'm wrong, that they quantize the KDV equation. But for the Dim equation, I don't know. But this is some future prospect. So such that the boundary theory, its Euler-Lagrange equation of motion yields the Dim hierarchy. That's the scheme. But this is not quantum gravity. This is gravity on its reduced phase space. If you are able to quantize this, it is quantum gravity on its reduced phase space, not quantum gravity completely. So this was my talk. Thank you for your attention.
Okay. Thank you, Kristiansen, for your talk. Very interesting. Let me stop the recording and we can proceed.